problem here.
Okay. So, starting with 17, so we'll go out of order about how we covered them. We last talked about chapter 17, and this actually, you can kind of see your review sheet there. And one of the things you're going to want to put on your note card or be familiar with this material is the 8 main eras. So there I've listed them. And I've kind of grouped the 3 main eras up there, the Planck, the gut, and the electroweak, because they actually are kind of differentiated just by the particles. There were no particles. Okay, particles start in era number 4 with particles, and then the beginning of nuclei and the nuclei, and then the era of atoms. And here at number 7, I noted actually, and this is something else on your test, that magic date after the Big Bang of 380,000 years after the Big Bang. So that's actually when electrons finally found homes around nuclei and formed atoms. And then the other thing I have noted, that last one, we are now in the era of galaxies. Thank goodness. Because if you're born anywhere else there, you'd be in trouble.
Number 4 is particle, right?
Yes, particle era. Yep. And this is actually this and the next one in their totality are available under doc sharing. Okay, so as a PDF, so you can print this afterwards. Oh yeah. So the thing about electrons finding homes around nuclei, this thing about 7, is that's actually when the universe became transparent, so that light could actually get through the muck. The fog lifted, as it's been described. Okay, so the next term there, the 4 forces, here today and had to have been present at the time of the Big Bang in some form or another. The first 2 are macroscopic. They kind of make sense. Gravity and electromagnetism. The other 2 are actually associated with atoms, cute little atoms, the strong and the weak force. You're like, who came up with that idea? You know. Okay. Then the next one, the cosmic microwave background and how it was first discovered. Actually, we saw 2 videos in here that kind of reinforced the Penzias and Wilkerson. I think that's their names. How they actually saw the hiss of the hiss of the universe being born, the hiss of the birth of the universe, okay, just using radio astronomy. And they were actually trying to track a balloon satellite. And I looked this up, I'm like, balloon satellite? That sounds like an oxymoron or something like that. I mean, it just doesn't make sense. But actually, communication satellite, they started it with using balloons instead of, like, we think of, you know, your metal communication satellite. So anyway, that's how they first discovered it. And the significance, okay, of actually the CMB and the next one, the relative abundances of elements in the universe, the significance of both of those are they support the Big Bang Theory. I love saying that, okay? They support those 8 eras, okay? So both the cosmic microwave background and the relative abundances of elements, they both support the what's known as the current cosmology, which is the Big Bang Theory. The next one, inflation, not anything to do with money necessarily, but I told you to kind of, with inflation in cosmology, think of inflating a balloon. So basically, faster than the speed of light, the universe very early, so this is after the gut era, and actually the first 3 or 4 eras were before 1 second was up even. Okay, so very early on in the history of our universe, the universe expanded very quickly. That's called inflation. And that actually, we talked about how kind of the perturbations of the little seeds that had formed before in the universe before inflation kind of became the seeds for galaxies. And then the last one, Olber's paradox. Okay, and remember, basically, when you think of Olber's paradox, think about a nighttime sky, and think that according to Olber's paradox, if the universe were infinite And if the universe were the same everywhere, if the universe always was, that means there's no Big Bang, then actually when you look out in nighttime, when you're turned away from the sun, it should be all lit up. Okay, that's Olber's paradox. Okay, so in other words, Olber's paradox suggests that since the nighttime skies are dark, then the opposite of what I just said is true. Then the universe must be finite, not infinite. And the universe is ever changing. Okay, so like I said, I'm going to go on to the next chapter, but this is available under doc sharing. And remember, as students here at SEC, you can print stuff it's not free, you paid for it. It's like when you go through a drive-through and they don't give you your stuff, right? You call them and it's like, oh, we'll send you a coupon for a free blah, blah, blah. No, it's not free. I paid for it. You just forgot to give it to me, right? Okay. So chapter 18, we have two darks. We have dark matter and dark energy, and what they have in common is we can't see them, but we can see their influences. So dark matter is not visible, but we can see the effects on other objects and actually the effect on light. And then in green, I have there that most matter in the universe is dark matter, instead of the baryonic matter, Star Trek term. The next thing there, we talked about how stars in the disk of the Milky Way galaxy and stars in the disk of other galaxies, they don't orbit like planets orbit the sun. So that's to say, basically, as you get farther from the center of our galaxy, instead of kind of going slower and slower, like planets go slower as you get farther from the sun, okay, they don't. They kind of even out. And the fact of that then, okay, I have here that orbital speeds flatten out going farther from the center of our galaxy, which suggests, bless you, that unlike our solar system that has all of the mass in the sun, basically within our galaxy we have mass everywhere. We just can't necessarily see it. So one of the things we talked about clear back in Unit 1 is that our Milky Way galaxy is surrounded by dark matter. Okay, well, you are surrounded. I posted a link on my Twitter feed because there's an article about how maybe we can see dark matter by flipping magnets. I don't know. It's kind of neat. So that was the second one. The third one, okay, this structure right here, this figure from your textbook, actually, those little yellow dots are galaxies, if not clusters of galaxies. And so remember that galaxies are organized into clusters, okay? And clusters of galaxies are organized into superclusters it's like somebody asked their kid, what should we call this? You know, our 5-year-old, and they're like, oh, I think we should call it superclusters, okay? And those superclusters are kind of on walls or filament areas around nothingness, okay, around what we call voids in the universe. All right, so 3 ways. How do you measure the mass of a cluster of galaxies? First is you can watch the galaxies within that cluster dance. And from their movement, you can kind of do what Newton said. Basically, their movement suggests a certain amount of mass. The other one is you can measure their temperature. Say, oh, I know, I can't resist. Okay, you can measure the temperature of a galaxy cluster and then backtrack that to the mass of the cluster. But my favorite one is the third one. Gravitational lensing basically goes back to what Einstein says, that any object, the denser and the more massive, the better. But any object rests on the fabric of space and time. Basically, it makes a dent in the fabric of space and time. So that objects behind this cluster of galaxies, actually we can see them because their light is bent. Okay, it's bent out and around. So we see an object over there even though it's here. Gravitational lensing. So the amount of gravitational lensing we can backtrack to the mass of the cluster of galaxies. The next two go together, machos, not nachos, and WIMPs. Okay, so machos are actually ordinary matter, baryonic matter, that might be part of what we call dark matter. Machos, the thing about them, massive compact halo objects. Okay, the thing about it is they just don't light up. So some dark matter is machos. Probably even more dark matter falls under the category of what we call WIMPs, or weakly interactive massive particles. Now, see, there's where, you know, people came up with some kind of cute little terms. Okay. Dark energy. Okay, so dark energy, like dark matter, is not visible, okay, but we can see its effects. Most likely, dark energy actually is what is making the universe not just expand, but its expansion to accelerate, go faster and faster and faster. We said F is equal to ma, so in order for any acceleration to occur, some force has to be causing it. Dark energy is most likely the force that's causing the expansion, the accelerating expansion of our universe. Speaking of, the last term up there, I brought this figure in from your textbook, kind of from left to right. We have 4 possibilities with regard to our universe. The first one is our universe could be recollapsing. The second one is our universe could be just what we say critical, and the size it is the size it's going to stay. The third scenario is basically our universe is keeping getting larger, okay? But actually the fourth scenario is what our universe is doing. Not only is it getting larger, but its expansion, or it's getting larger, is accelerating. Okay? So recollapsing, critical, coasting, and accelerating universe. So under green there, I kind of said with regard to the amount of matter at the time, the universe was all one cute little thing called singularity, okay? At that time, how much matter was there relative to the second scenario? So we really don't think we're going to need the big crunch. The big crunch is the recollapsing universe, because we didn't have that much matter present at the time of the Big Bang. Okay, the critical one, where it's going to stay the same size, that's probably not likely either, because like the last 2 scenarios, we definitely think that the amount of matter at the time of the Big Bang was less than critical. So that leaves coasting or accelerating. And like Hubble, Edwin Hubble found, and we talked about this clear back when we talked about raisins, back in Unit 1, our universe expansion is accelerating. So not only did we have less than the amount of critical matter at the time of the Big Bang, but we've got dark energy driving that acceleration. It's almost like they're ganging up on us. All right.